unspec all these icons from the computer. What on earth? All right, let's get this. Get OneNote up and going here. Oh yes, we were doing net change. I sitting in chapel going, I wonder what we were doing. Now I remember. Yeah. How are we doing? Give another minute for those who are straggling. Just one more minute. All right. All right. Whew. All right, everyone. Well, we're missing. Oh no, Leah's almost here. Leah's almost here. I see him. Oh, I have exams to give back now. I'll remind me to do that. Remind me to do that later. I um I was supposed to submit midterm grades like a few weeks ago and I forgot. So I submitted them on self-service, so if you're curious, but it's basically whatever's on Moodle. So whatever, whatever's on Moodle, that's what gets submitted. This class, I updated some of the WebWork scores so that they were accurate, so you can get an idea where you're at. If you are struggling, just reminder, I sit in my office all day waiting for people to come by and talk to me. I'm just sitting there, nothing to do. I'm writing a paper instead. It's a nice paper, but if you want to have me do something, more related to what your own work, I'm happy to do that. Okay, so let's just sort of recall what we were doing. We were using these definite integrals to compute something like displacement. In fact, that was our first example, was to compute the displacement. So we had a particle that travels along a line, and there is a velocity given here, a velocity function, and we want to know the displacement of the particle between time 0 and time 6. And so to compute that, we literally just took the integral of the velocity function. The other way of doing that would be to, find the s of t function, the position function, plug in at 6, plug in at 0, and take the difference. But we can simply do this definite integral instead. And so we take the antiderivative, we get this, we plug in 6 there, we plug in 0 there, it comes to 18 meters. And this idea of displacement can be generalized to other settings. It's called net change, and it just sort of tells you how much a quantity has changed from one time period to another. And the formula for net change is basically the same as what we had for displacement. You just integrate the derivative of the quantity that you want to find the net change of. And so we did an example with a balloon that's filled with helium at 9 a.m. We were told that it leaks helium at this rate. This is sort of our rate of change. And we're asked how much helium is lost between 1 p.m. and 4 p.m. And so we let S represent the amount of helium lost at time t, as of time t. And we're told what S prime is. And so we simply just integrated over the appropriate interval and got 2.4 liters. And so that's that. And we had left off with doing a few more problems here. Related to this, I worked out number 1 at the end of class, but there's more to come here. I'm going to make copies of this down here at the bottom. Right there, I'll make a copy there, and I'll put the squirrel problem next to it so that you can see, maybe not both of them entirely. You can see a good thing. There's this thing called bring forward. I don't know what I'm doing here. There, that work? Yeah, sure. Okay, so hopefully you got something to get started with. So let's take a look at number 2, and I'll just leave you to it here. So you have a tank of water. You're told the rate at which it's leaking. You're asked to find out how much has leaked, how much water is leaked between 3 equals 3 and t equals 8. So go ahead, try these out. Just try a bunch out, see how it goes. If you need to see number 4 eventually, I can kind of move things around so it's easier to view. But yeah, we'll just get started doing problems. Not a lot for me to talk about right now. And yes, I want to remind you, you can be social in this class. So I know that many of you are deep down inside aching for a calculus friendship. You can make that happen by taking the first move. Yeah. How's it going? Good, good. Yep. Okay. I'm just wandering about the room, waiting for someone to talk to. I'm just don't worry about me. I just have nothing to do. I'm just like spying on people. I always love those multicolored pens. I think I had one like that as a kid. I was just like, this pen is amazing. How's it going, Liz?
Trying to remember.
Okay. If you need further help remembering, I am here. I actually remember all of this. I do, yeah. That's what happens when you take this course about 7 times. You're gonna remember it all. How's it going? Looks like you got started there pretty good. That final number is a little different than what I have, but everything looks right. It might be that, yeah, I see what it is. You're in degree mode. Switch it to radian mode. There we go. Now we got the same answer. Yeah, I'm trying to find the antiderivative of sine.
Just negative cosine.
Negative cosine. That's it.
When do we do the 1K cosine?
Uh, next slide pack, I'll describe how to do that some more. But for now, you don't need to worry about it. Okay. Yeah, after this topic, I'm going to go over something called substitution, which is a way to do even trickier integrals. Very good work. Yes. Okay. I'm just looking at. Just want to make sure you have the right number in the right place. All right, Liz, have you remembered? Pretty much. you are unfortunately, so this is actually what S prime is.
Okay.
That you're given the S prime and then you gotta do the integral of that from 3 to 8. And then you gotta worry about the cost of widgets. In number 3. Widget production is quite complicated. I don't know. I'll still leave it here for now. Eventually if you need to see number 4, eventually let me know. I'll zoom out so you can see it. How's it going, Megan? Yes, that's the correct antiderivative. I don't know if that's the right number. Oh, you're still in the process. Okay, very good. Hey, I got that too, yeah. Online students, don't forget, I am here with answers. If you're like, man, I need to know the answers to these questions, don't you worry, I got them. One of these days, I'm gonna find out if ChatGPT can do all my group work problems. I mean, it's a reasonable question to ask, right? Actually, let's. Curiosity is getting the best of me here. Hold on. I want to know. Inquiring minds want to know. Can ChatGPT do net change problems? What would you think if it did? That'd be kind of scary, huh? When I first checked it, it couldn't do them. But maybe it can now. Okay, everyone. Let's see what ChatGPT says the answer is. The number 2. I went and I stuck it in there. You may be wondering what all of this weird $sign stuff. This is a math typing system called LaTeX or LaTeX, and ChatGPT can understand it. So I gave it this integral. It correctly set up that it's square root of t plus sine t. And then it's like, okay, I need to do this integral. That is correct. That's exactly what it should do. It even correctly takes the antiderivative. It plugs in at 8 and 3. That's correct. That's correct. It finds a common denominator. That's correct. And then it does it for the sine term. That's correct. Correct. But strangely enough, somehow it screws it up. It says it's 0.8285 liters. And the answer is 10.7764. So not quite there yet, are we? Came close. It had like all the elements there. It just. I think it just can't do arithmetic. Your answer is incorrect. Can you find your mistake? Certainly. Well, we'll see. We'll see. All right, folks, I still have a job. So we all still have jobs. And yeah, it's gonna just repeat what it just did. All right, I'll let it do its thing. Yeah. You're like, me and ChatGPT actually agree, Brandon. You ever considered that maybe you're wrong? You have to be in Radian mode. But that shouldn't substantially change it. So
I could just put it in the calculator wrong.
that's what it looks like, because everything you have there looks fine. You struggle with the same thing ChatGPT struggles with, actually evaluating things numerically correctly. Do you have an answer for, oh yeah, I already checked your number two. Do you want to check anything here? That's correct. It should be a positive 3/2 in the exponent, so it should be t to the positive
Okay.
3/2. Here, I know what I'll do. Yeah, that'll look better. Hopefully you can, yeah, I think that'll. How's it going, Keaton? The 375 is correct. 25,000 is not. Interesting. Interesting.
I did again. It's still, I don't know if I said my equation right, because I keep putting it in.
No, it's correct. Oh, you're right. It's incorrect. That should be a 3/2. 2/3.
so I
Yeah,
put it-
okay. I hadn't noticed that. Number 3 has some confusing terminology that I probably should go over here. This is like the terminology that's used in economics and business. So we're gonna let C of X denote the cost of producing X widgets. What is a widget, you ask? I don't know. You can you can think of a widget as a mousetrap. A widget is a plunger. A widget is just something you make in a factory, okay? And it costs money to make. And so there's a cost of producing a certain number of widgets. So you can imagine this function, like you ask yourself, well, how much is it going to cost for me to make 100 widgets? Well, you take X, replace the X with 100 and whatever this formula is, and that'll tell you how much it costs. The derivative of this is what's called the marginal cost. And so if you wanted to know if I want to know the cost of increasing production from, say, A widgets to B widgets, it's really just C of B minus C of A, or equivalently the integral of C prime of X. Hold on, wait, I haven't gotten to part B yet. So I tell you what C prime of X is. And basically part A is just asking you to do this integral. You just plug in what that quadratic is and you do the integral from 15 to 30. But then part B gets a little bit harder. There are multiple ways of doing this. And I'll let you sort of think of the one that you think makes most sense. I ask in part B, what is the cost of producing 20 widgets if C of 0 equals 2000? So if you're working in a factory-like setting, there's a cost to setting up the production line to run. Like it costs money to just even get started. And then after it gets started, there's a cost that goes through and it's not as bad. And so I'm saying, well, imagine like the startup cost is $2,000. How much would it cost to produce 20 widgets if you had to pay $2,000 just to even begin production? So go ahead and try those out. I admit not exactly the most thrilling problems, but give it a go. See what happens. And if you get through there, we have a squirrel that's moving. It's terrified. Doesn't know what to do. You can help save the squirrel. Here, I'm gonna move this here. There we go. There we go.
Because if
Well, do
this
part A
is-
first.
I did.
Oh, very good. Yeah.
So if this is the integral and the integral is the opposite of derivative, you find C of X versus C of X, C of 0, you plug in 0. And
So
you get-
there's two different ways you could go about this. One is to just do the integral from 0 to 20. Find out how much it would cost to go from 0 widgets to 20. and then add 2000 to that. Another option is to take the indefinite integral. Find out, just do the antiderivative, you'll get some constant, solve for that constant. So there are two pathways afforded you for part B. Yeah, yeah, you're in degree mode when you're plugging in for your sine. Yeah,
But this is correct, right?
yeah, that's correct. It's just your cosine is in degree mode, should be in radian mode
Okay.
on your calculator. I recognize that as the degree mode answer. How's it going, April? Any questions? You take very good notes. Were you able to get an answer for part A? It should be 375. So I don't think that's quite it. How's it going, Keelan? Very good. Yeah, it's hard to stay awake sometimes. I feel it too. I start yawning. No. Oh, you did not get a lot of sleep last night. Oh. Unfortunately, yeah. Oh, I have plenty of time.
This is calculated in degree mode. I don't want to change it because 'cause this is what I used to get this one. And it's
That's a good question. There's. Oh, that's fine.
I got this from
Well, I don't know how to get it in degree mode either. Out of degree mode. No, on his app, different. I know how to do it on a TI, but not on his thing. So for part A, I'm kind of like writing it all here at the bottom. You should have gotten 375 widgets or $375, $375. Yeah, a big part of it is taking the antiderivative correctly. A bigger part of it is actually plugging it all in a calculator correctly. Don't feel bad. ChatGPT screwed that part up too. So. Oh yeah, it should be 400x. Yeah. Oh dear. Even ChatGPT wouldn't get that wrong. All right, so it'd be 400 times what? Let me move stuff around here. 400 times 30, and then yeah, let's just erase. 400 times 30 there, minus 400 times 15 there. It's still 375. Okay, so that's for part A. For part B, I want to sort of discuss this one because yes, that's correct. For part B, we kind of have two options. One is, so option A, would be to solve for C of X. Like just figure out what C of X is. You'll notice that when we did part A, we never figured out what C of X was. We just did C prime of X. And so we could do that. The key though is to recognize that we are not using definite integrals at this point. We are using indefinite integrals. They are very closely connected. And really the only difference between the indefinite integral and the definite integral is that with the indefinite integral, I now have a constant present. Now, normally I write that constant as a plus C, but I'm already using the letter C for my function name. So when you can't use the letter C, you use the letter K. Why do we use the letter K? I'm not really sure. I don't know. It also makes a K sound, so might as well. And then what we could do is we could take a look at this information we're given. We're told that at time 0, we should have 2000. And so if I plug 0 into all of this, I'll get a 0 cubed over 3 minus 20 times 0 squared plus 400 times 0 plus K. Well, that's just going to be K. And so if I need C of 0 to equal 2000, my K better equal 2000. And so now I have a really nice C of X here. And if I wanted to figure out, oops, I started looking at the wrong thing. If I wanted to figure out what the production cost is for 20 widgets, I could just plug in 20 and that'll give me my answer. So I mention this because there are times when you can solve a problem easily using an indefinite integral. And there are other times where it's a little bit easier to solve it using a definite integral, but both can give the correct answer. And that's what you should get. Cost is $4,666.66. 67 cents if you round. Obviously, these are some pretty nice widgets as far as widgets go, like really good. The other option for solving this problem, option B, is to just compute the following. Say, all right, it's going to cost me 2,000 no matter what. And let's do this integral from 0 to 20. I start off producing no widgets, and I'm going to integrate C prime of X dx from 0 to 20. That'll work too. Do not write this in your homework, equals dot dot dot. You get the exact same answer. All right, ready to study the squirrel? Any questions on this I should ask? Yeah. 375. Okay, so just so we're clear what's happening here. We have a road like this. And there is a car driving towards our little squirrel. Let's that's not a very good squirrel head. There, that's better. Alarm. Did I ever tell you students about the time I saw the weirdest squirrel in my life? I did. Okay, good. It's important. If you ever see a squirrel like that, let me know. Because I still don't know what to make of that. Such a weird situation. People have moments in life where they experience the paranormal or the unusual. But the problem with my experience, it was just too weird. Just too weird. It's like, this isn't any fun. All right, well, that's a squirrel, and believe it or not, it hasn't been run over yet. And we've got a car coming towards it. And so the idea is the squirrel's sort of running left and right everywhere along this road. This is our road. And you're asked to do a few things. You're asked to find the displacement. You're asked to then figure out the points in time where the squirrel changes direction. Have at it. I'm gonna work on the squirrel. I'm not very happy with him. Kind of looks like a. There we go. I once drew a perfect squirrel in class. I haven't been able to draw one since. And there he is. Oh yeah, draw him big and then shrink him down. Yeah. You'd think I'd be really here. We'll try it. We'll try doing it this way. I look like a squirrel tail to you. I don't know. Yeah, I'm imagining a squirrel foot's big. Yeah. That's got his little grimy paws there. And kind of have this sort of, am I right? Like this is kind of how they look. Yeah. Do they have pointy ears? No. There we go. That's looking better. Give him more of a. All right, nice. Right there. No. Just nostril right there. It kind of looks like a mixture. Oh, yeah. There we go. In case the drawing wasn't good enough, perhaps the color can be like a cue. And you're like, yeah, I guess I see that's a squirrel. Yeah. So, there we go. All right. Good idea there, Liz. Draw a bigger squirrel and shrink it down. Yeah, there you go. Now the highlighting's all off though. All right. Where's the squirrel and yeah, here we go. Yeah, it's not looking good. Not looking good for our little frontier. Not looking good. Hard to draw this in perspective, huh? Kind of hard. There we go. Yeah, there we go. This is a bright red car. There's the looming death. Windshield right there. There we go. Car looks better. It's kind of an aerial view. Okay. Wheel's a little off there. Oh, are you already given the integral? Yeah, so S prime of t is v. So if S is the position of your squirrel, then S prime is the velocity. So you are going to be just integrating this function from 0 to 5. It should just be negative 0.833. Like that squirrel's not going that fast. Squirrel's not hauling. Right. So if I want to compute the displacement, it's pretty straightforward. In theory, I just got to take this antiderivative, right? So I'll have a t cubed over 3, a minus, well, I guess it'd be a 5 over 2 t squared plus a 4t right there. Evaluate at 5 and 0. I liked hearing President Mullins Chapel today. Her story about Kay Lindley, that was hilarious. For those of you who don't know, Kay Lindley is Mike Jordan's grandmother. Multiple layers of grandmothers going on here. So when I compute 5 cubed over 3 times 5 halves times 5 squares plus 4 times 5. Well, did anyone get an answer? What does all that equal? I know Keaton has it. 0.84. Thanks. I stole your work. Yeah. I guess we should have a unit here. It'd be feet. So this is a situation I've encountered in real life where I'm driving a car and I can see a squirrel, sees that I'm coming, and the squirrel is like, I will run off this way. No, I'll run off that. No, I'll run off this. No, I'll run off that way. And then 5 seconds later, it's only really moved a foot or so. It's just having a tough time deciding how it wishes to evade my car. Have you ever experienced this? The indecisive squirrel? Yeah, I have. You feel bad for him. All right, so that's a displacement. So from our perspective, we might think, wow, the squirrel has not moved much, but no, it has. It has. And we can see that by plotting this function. So let's get away. Yeah, geez. No, you are still wrong. I'll give you a hint. You made a mistake doing math. There. We'll let it keep going. All right, so this function is t squared minus 5t plus 4. I'll write v of t. T squared minus 5t plus 4. Okay, so here's our function. We're interested in the interval from time 0 to time 5. Do any of you see when does the squirrel change direction? 1 and 4 is correct, right? Here, the squirrel is, maybe we'll assume positive velocity means running to the right. Running to the right, slowing down, then going to the left. Moving to the left, moving to the left, slowing down, then moving back to the right. So it's not too erratic. It's just zigzagging, once or twice. All right, so using this plot, we can see that it changes direction at time 1 is 1 and time 2 is 4. And so now what I ask you to do is not exactly the most thrilling sort of computation, but it needs to be done. I need you to figure out the integral of this velocity function from 0 to 1, from 1 to 4, and from 4 to 5. Yeah, have fun with that. I have to make you do it here because I give it on homeworks, and if I don't make you complete it here in class, you then come to my office and you're like, oh no, how do I do this? Mhm. Oh, you got yeah, that's. Is it negative 0.83? Did I write down the wrong thing? It is negative 0.83. Oh, no. Keelan's correct, everyone. I did math wrong. Keelan's like, I don't know. I got negative 0.83. You're right, Keelan. You're right. I do have more slides. Exponential function slides. Great. I want you to notice that you can have a little bit of a shortcut here. When I do this integral from 0 to 1 of VT, I've already figured out an antiderivative here for my VT, right? Right there. And so really what I'm doing is I'm plugging in 1 and 0 into that function. And that's it. Whoops, I started sliding away there. I wonder what that simplifies to. 1.83 repeating. That's what I got for that first integral. And I can try doing it for the rest of these. Integral from 1 to 4. A little glitch there. So anyone got an answer for the second integral here, the one from 1 to 4? Well, what'd you get, Lee? I got negative 4.5 as well. It's probably just a little mistake somewhere. I love it when everyone gives wildly different answers. Oh, you just did it in Desmos? Yes, Desmos is a great tool for making fast work of this. And now you can be like, and I'm really sure it's right, folks. You wanna know why? Yeah. All right, and if you do the integral from 4 to 5 of V of t dt, it will also be 1.83 repeating. I'm kind of skipping that part. And so if we take a look at these here, maybe I'll color code stuff. This is this integral here, and we got 1.833. This is this integral here, and we got -4.5, and this is this integral here, and we got 1.833. All of these units are in feet. So now the question is how far did the squirrel travel? What was the distance traveled? So any idea on how we figure out the distance traveled by the squirrel over this interval from 0 to 5? I guess this is technically part C. Absolute value signs, says Sydney. Yes. What we're going to do is we're going to say, all right, well, we did these integrals where we knew the squirrel changed direction. And so if we want the distance traveled, what we're going to do is take the absolute value of 1.83 repeating plus the absolute value of -4.5 plus the absolute value 1.83 repeating. We're basically taking the absolute value of all those integrals and just adding them up. And that will give us a sense of how much pavement did this squirrel cover in that 5 seconds. And it turned out that the squirrel had a pretty good hustle, got 8 feet got 8.16 repeating feet. So that's the idea there. Any questions on this concept on how we compute distance traveled? Now there's another way to view distance traveled, and we can see what it is by plotting the absolute value of V of t. So if I do absolute value V of t, actually, no, that's not how it works. I guess I just do the absolute value sign. Yeah. Oh no, it's not going to let me. Here, here it's an X there. Does that make you feel better, Desmos? It does. So there's the red one. That's the one with the out the absolute value sign. Here it is with the absolute value sign right there. And we could ask ourselves, what is the area under this blue curve? And it's kind of neat because you can actually get Desmos to do this. I'm trying to remember how it works, but is that how it works? Or maybe it goes the other way. Or maybe it goes this, yeah, that's how, okay. There we go. Good job, Desmos. I can do it. All right, so you see that right there? We've got this shaded region under here. Now, does anyone want to speculate as to what this green area is equal to? What was that? Yeah, did you say 8.1? Yeah. The area under the absolute value of the curve is going to be the exact same thing as the distance traveled. That's essentially what we computed. So this'll, all that to say, this is distance traveled right here. Now in practice, it's useless to do this. The absolute value function is hard to take the integral of because it has these kind of weird cusps, these points, right? So you can't just take the antiderivative of it so easily. But in practice, we could achieve the same thing using the method I described here. So now you're ready for a homework problem I have that's very similar to this. Any questions though, before we move on? Okay. So I'm gonna add a new topic here. I probably should have done that earlier. You can tell we're running low, folks. I got substitution, natural log, and exponential. I'll make sure to bake in a healthy amount of review for this course, but I get to cover some other things as well. So I might cover parametric. Basically, what I'm going to do is cover topics that I think will help those of you who are going to take Gen Phys 1 eventually. Because I think that's sometimes a difficult course to handle. All right. So you can see I have some content there under the on the slide here. I'm going to try to reveal it slowly, slow reveal. All right. Imagine I were to ask you to do this integral, just the indefinite integral, just find the antiderivative plus a constant. You're asked to do this for 2x cosine x squared. In other words, you want to find a function that when you take its derivative, gives you this. Now this is really hard. Though many students think they can find a clever way to do it by doing the following very illegal operation. Sometimes people will be like, I know how to do this. I have an integral of a product. I will just break it up into a product of integrals. This is illegal. You can break up a sum of integrals you can break up a sum that you're integrating into a sum of integrals, but you can't do it with products. It doesn't work that way. It's an epic fail, as one of my kids would say. He's big into fail videos. Sometimes we'll be at the grocery store and someone will drop something. We'll be like, Mom, that's like an epic fail. We try to just move on. So how do you deal with integrals like this? Like 2x times cosine x squared? Well, to be honest with you, let me be clear about integrals in general. The reason why you've been able to do the integrals you've seen so far is because I gave you the easiest possible ones. I have that doing integrals is just incredibly difficult in general. Like there isn't any good way to compute integrals that works all the time. And so what we learn is like a series of techniques that work for some integrals, but not others. And so the technique I'm going to teach you today, or at least introduce you to, is called substitution. And it's basically based on the chain rule. So one thing you might notice if you're incredibly clever, and maybe that's you, maybe you looked at that 2x cosine x squared and you're like, oh, I know the antiderivative of that. That's easy. You were like, look at sine of x squared, right? If I had to take the derivative of the sine of x squared, what must I do? Well, you must use the chain rule, right? And so you could say, oh, okay, all right, well, I'll take the derivative of the outside function. That'll give me cosine x squared. And then I have to multiply by the derivative of the inside. That gives me 2x. Bam, there we go. 2x cosine x squared. And so you could say something like, yeah, it's just the antiderivative of 2x cosine x squared is just sine x squared. And that's assuming, of course, you're brilliant, right? And you're able to just be like, oh yeah, of course, that's the chain rule in reverse, obviously. But what if you're not brilliant? What if you don't know how to do the chain rule in reverse? Let me teach you, okay? Unfortunately, the scrolling has failed on OneNote. I have to close it and reopen it. That happens sometimes. Not sure why. Let's do an example.
Just take the inside function. If you know it's from the chain rule, then you just take the inside function and find the antiderivative of.
Yes.
Don't worry about the formula. I'll show it to you later. Don't worry. Let's suppose you're asked to do this integral. How to do is the question. How on earth do you do this integral? Well, what we're going to do is use a technique called substitution to help us see how this is the chain rule in reverse. And the key to using substitution is to identify the thing that gives you the most problems in life. Now, I know the antiderivative of sine. I do not know the antiderivative of sine x cubed. The thing that is giving me problems in life, it's that x cubed. This is the problem. Maybe not problem, with the complication. It's not immediately obvious how you do an antiderivative with that annoying x cubed there. So what you do is the following. We are going to let u be x cubed. In other words, we're sort of creating a new variable that we're calling u, and we're going to work with this variable u instead. Okay. And so what I'm going to do is I'm going to take that integral there. I'm going to have to write some more stuff here beneath. I'm going to take that integral there, x squared sine of x cubed dx. And I'm basically going to replace this sine of x cubed with a u here. And well, I mean, what do I do with these things? The x squared and the dx, those are different letters than u. How do I deal with that? Well, here's the trick. Let me show you the trick. What I'm going to do is I'm going to take the derivative of u. And we have two different notations for derivative. One of them is just u prime, and the other one is du over dx. And I'm going to use the du over dx notation. And so what's the derivative of x cubed? 3x squared. Beautiful. And now here's the thing I notice. Do you see that x squared there? I got an x squared there. I'd like to not have be there. I also have a dx here. I'd like to not be there. And this is where we do something that's slightly illegal. Du and dx, we are going to tear asunder. Normally they come together in pairs, the du and the dx. But now what I'm going to do is some symbolic algebraic manipulations. I'm going to multiply by dx on both sides. By the way, if you're a mathematical purist, your heart should be breaking right now. And then I'm going to divide by 3 on both sides. When I saw this as a student, I was so sad. And the upshot of doing so is that I can see that this x squared dx that I have here is the same thing as my du over 3. I don't know. How do you feel about this? Should feel a little uneasy here. Just a little. You should be like, I don't know about this. This feels kind of like you'll be surprised how quickly you get acclimated to this. It's kind of like lately I've been watching videos on cults. Because I mean, why not watch a cult? How does a cult get started anyways? And at first people get into the cult and they're like, yeah, this is kind of weird, but then like within a few months they're like, totally, this is normal. Praise the leader. You know, they're just totally, it's just like it was never weird to begin with. That's exactly what will happen to you with substitution. You'll become completely brainwashed into believing it makes sense. I can't wait for the course evaluations later. Okay. All right, so I have this 1/3. What's the antiderivative of sine? Cosine, right? And now I don't have that annoying x cubed in there. So it'll be a negative cosine of u plus a constant. And then the cool thing is, I then have that my u is x cubed. And so I get a negative 1/3 cosine x cubed plus a constant. And that's my antiderivative. Okay, I've introduced you to a new dark art. We will practice it some more. It's so weird the first time you see it, but you get used to it. I'll give a rigorous justification for it later. Online students, I hope I haven't disturbed you with my crazy math there. Any questions before I hang up? How would you figure out the length of the line on a function? We talk about area, not length. Ooh. So there is a complicated formula for that. I can do it when we do parametric equations. How's that sound? I can do it then. Okay. All right. All right. Well, I'll see you folks later. Bye.